Yo, YouTube, it's your boy. What is this boy? It's your boy JOHABRAHAM in the flesh, son. In the flesh. Oh shit. Intro to general chemistry. Boy, where is it? General chemistry, son. Okay. Courses in English. What? Okay. What the fuck was this? What was the last thing I learned? I remember orbitals. Hey Devoto did appreciate for checking out the stream. I believe the mic is working. Yes, the mic is working. Where is it? Yep, orbitals. F orbital, atomic orbitals and quantum numbers. The shell with principal quantum number consists of exactly n subshells. Like if it's a if the principal quantum number is 4, then it's gonna be s orbital, p orbital, d orbital, and f orbital. Is that how it works? I guess. Hi, Crakathumb Josh. Hey yo, what's up? I appreciate the comment. I believe, yeah, the screen is working. Yes. There's no space between crack thumb. It's a single name. It's Crakathumb. And I'm not using my cameras because it's pretty dark up here and I don't want to turn on the lights. So no cameras this time. No. It's orbitals and quantum numbers. So if the principal number is 4, then we should be having S, P, D, F. Oh, ChatGPT is so slow. Consists of 4 subshells, okay. Number of orbitals per subshell, study with GPT. What are the things that are mainly mentioned here? Orbitals and quantum number. Oh wait. Hey, so that timer for 30 minutes. Why would my phone hear this? God damn it. God damn it. God damn. Here is the direct, clear meaning of each bullet point. The shell with principal quantum number. I got this one. Each subshell consists of specific number of orbitals, whereby each orbital corresponds to different allowed value of mi. There are 2l plus 1 values of mi ranging from -1 -l or example for s l equals 0, 1 orbital. For p l equals 1, 3. Okay, this is the formula that 3 orbitals, 7 orbitals. Wait. minus 1, and this basically shows the spin of the orbital, or the magnetic spins in that subshell. Total number of orbitals in a shell is n squared. The total number of orbitals in a shell is n squared. This is just a sum of all the orbitals in that subshell. If the shell n one orbital n is equal to 2, 4 orbitals. How? Oh, 3 plus 1. Oh, that's cool. No, be precise about what each quantum number actually means, because mixing them up will destroy your understanding later. Damn. ChatGPT is telling me to be precise, okay? Here's the correct interpretation. L is not n minus 1. L can go from 0 to n minus 1. Oh, okay. Example, if n equals 3, L equals 0, 1. It's not equals to n minus. It's just the maximum possible values. Wait. What? Uh, M1 does not describe spin. M1 describes the orientation. Okay, that was not the spin, it was the orientation. Orientation of the orbital in space. Orbitals can point in a different directions. That's why MI ranges from -1 to +1. Total of 2L plus 1 possible orientations. Okay, possible orientation. Yeah. Spin is different quantum number. Spin quantum number is +1/2 plus. Each orbital can hold 2 electrons because of these 2 spin states. Okay. What the examples show? Okay. Could you? Okay. Now let's take the carbon atom as an example, and could you tell me all the details for 1C atom of atomic number of 12? Wait, carbon is 12, which means it has how many 12 which means n equals 12. Let me see if that's true for carbon. It's just a problem. This is a problem. It's Z. For carbon 12, here are the correct facts. Atomic number Z equals 6. 6 protons, 6 electrons in a neutral atom. Mass number is 12. I'm sorry. This was the mass number, okay? This does not mean n equals 12. N comes from the electron shells, not atomic mass. Electronic configuration of carbon Z equals 6. Aha. Aha. Periodic table. What about nitrogen? Oh shit, I got it, I got it, I got it. I understand. I understand. So we are considering the atomic number and we're distributing the atomic number. Atomic number shows the amount of number of electrons. Shells used n equals 1. Carbon does not have electrons in the shell. N equals 3, 4, 5, 12, only up to n equals 2. Subshells and orbitals involved. One is, yeah. Two is subshells, electrons, yeah. And 2p, yeah, I know. And each of these would be having plus 1. Oh. Why is this empty? Oh shit, 2p has the potential to take in 6 electrons, but only 2 is filled up. Yeah. So most relevant here would be atomic number, which directly the number of electrons enclosed within the atom on their subshells. Yeah, I believe the atomic number is the most important one. Bro, ChatGPT is slow as a Okay, that's basically it. Each subshells consists of a specific number of orbitals, whereby each orbital corresponds to a different allowed value of m. Can we say half of the atomic mass? Yeah, we could say half the atomic mass, okay. It's pretty cold. Let me heat up my hands. Devoto did. I'm gonna be refreshing the chat because it's better not to have anything written up there. Okay. Could you again briefly let me know the terms involved? Spin the. Wait, the spin? What? Okay, principal subshell n equals 3. Uh, uh, I'm a bit confused, a little bit. Ooh. So n equals 3. Shell quantum number denotes the main energy level of an atom. Higher n electron is farther from the okay. Subshell determines the shape of the region where the electron is likely to be found. Uh, Orbital magnetic quantum number, specific orientation of the subshell in space. Okay. Okay, I understand this one. Yeah, yeah, yeah. I understand this one and this one. Spin. That's just either one, the plus or minus. Electron configuration, distribution of electrons across shell, subshells, orbitals according to n energy levels. N and I are two characteristics finds the allowed energy level. Only discrete quantized energies are permitted, which corresponds to electron occupying standing waves orbitals. So the hierarchy is shell, subshell, orbitals, spin. There's hierarchy. Okay. Can you name me an atom, an element with its I'll try answering what I have. Mm-hmm. Element phosphorus, mass number 31. Ah, shit. Here we go again. What would it be? What would it be? Let me do let me do this on my own. Wait, are we going for mass number or just give me the mass number, bro. Weight isn't atomic number relevant here. $15, okay. One S, two S, two P, three S, three P, 3D, 4S, 4P, 4D, 4F, 5S. Okay. Mm, 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D. Okay, okay. So 2, 2, 6, 2, 10, 12, 3. Okay. So it's 1S, n equals 3, and so I found out that n equals 3 and 1s, 2s, 2p, 3s, 3p, Good attempt. You're almost there, correcting and clarifying step by step. Yeah, 3p3. Okay, okay, okay. Breakdown. 3p subset detail. Hunt's rule. It's either top or bottom. Yeah, yeah, yeah. So are so there are three unpaired electrons in the phosphorus, making p paramagnetic. Quick counts. Why? What? Oh, okay. So the valence based on the You know what? It's pretty cold. I'm gonna close the fucking curtains. Curtains. God damn. Cold. Oh. Stop. It's 30 minutes. Guess what? Push up time. Yes, that is the correct way to think about valence electrons. Okay. Push up time. Push ups. fuck is this? Ads? So what are the things? Okay. On the part where the 4S and 3D, but oh, any single three. Okay, okay. That's based on Aufbau principle. Now, why does this seem confusing? Because forest fills first. Oh, this okay. Magnetic quantum numbers only describe the shape. Okay, okay, okay. Um, what was the paramagnetic property of phosphorus. Like, what are should have at least one unpaired electron. Diamagnetic. So, what is this paramagnetism and di? When you apply an external magnetic field, those tiny magnets try to align with the field just like a compass. Material is pulled towards the magnet. Oh shit. Oh. So with odd atomic odd not mass. Each each orbital can hold a maximum of 2 electrons. These electrons behave as they would spin around their own axis. Odd atomic number increases the chance, but it's not a reliable rule. Why? If an atom has an odd number of electrons, then odd number cannot pair all electrons. At least one unpaired paramagnetic. So yes, odd numbers often means unpaired electrons, paramagnetic, but many odd atomic number becomes diamagnetic. Helium, lithium, but those are ions. Oh shit, oxygen. Okay, okay. Wait, so if I understand, so okay, okay, I agree. But if an atom unpaired could you explain this on the basis of uh, waves as magnetic field is a wave and electron does have wave like property, but paired results different. Different or opposite? That's really interesting. Like Aufbau principle of electron show. Can I? Oh, I can. Fuck this, bro. Every electron is a tiny magnetic dipole. But quantum mechanical intrinsic angular momentum. Spin produces a magnetic moment. Magnetic moment equals a tiny bar magnet. So every atom, every electron has a north-south magnetic field on its own. When two electrons pair, their spins are opposites in the same orbital. Each electrons must pair. Their magnetic moments are equal and opposite. They cancel. Net magnetic field zero. That's why paired electrons show no magnetic behavior. Oh, it's not repelling. It's just no. Okay, okay. Now the wave explanation, the one you asked for. Quantum mechanically, the electron is described by a wave function. The spin part of the wave function has two solutions. Spin up state, spin down state. When two electrons occupy the same orbital, their total wave function must be antisymmetric. Okay, so for spare electrons, spatial part is symmetric, spin part is anti-symmetric because spin wave function cancel, the magnetic field contribution cancels. This is the wave-based reason. Spin wave function interfere destructively, just like destructive interference of water waves that kills the magnetic moment. For unpaired electron, there is no second wave to interfere with. Why does the magnetic field attract unpaired electrons but repel paired electrons? Why does magnetic field? External magnetic field aligns the magnetic dipole with the field. Lowers energy. System is drawn into the region of stronger field. An induced magnetic dipole appears. It opposes the applied field. This opposing field weaks repulsion. This is purely from wave function reacting to the. This is purely from the wave function reacting to the changing electromagnetic potential. Summary in simple. External magnetic field interacts with the spin part of shifting energy levels, Zeeman effect. Wait. So it's attracted and wait. Don't worry. I can't comprehend this. Come on. So paramagnetism, unpaired electrons. Uh, what was the other one? Diamagnetism. Exactly, diamagnetism doesn't mean a material is actively repelling a magnetic field like a magnet pushing another magnetic way. magnetic way, it's very weak response. When its external magnetic field is applied, the electron orbitals motion slightly adjust to create an induced magnetic field in the opposite direction. This effect is extremely subtle and generally negligible compared to the paramagnetism, but it doesn't mean the material weakly opposes. Oh. Mm-mm. So if we show magnetic field to a paired electron outer shell, it tries to repel. It tries. Okay. It's a lot to take in. Wait. Mm. So mhm. Mhm. It adjusts the spin in a way that it makes another magnetic field. But wait. So if we enough external magnetic field, the induced magnetic field produced by the paired outer electron shell will produce a repelling effect. Enough. Enough. Wait. Wait. Not gonna lie, it's pretty cold. What the? Yes, in principle, when a strong external magnetic field is applied. Hmm. It's interesting. Wait. So it's changing. Okay. So let's consider the entire Earth and its magnetic field, and both elements that show paramagnet and dia all those are following following, not following following. Okay, okay, I get this. I get this, but I cannot find the reasoning for. Yeah, that makes sense. That type of answer. When you apply field, exactly, you can think of Earth's magnetic field as a very gentle, uniform field acting on all the atoms around us. Paramagnetic atoms get slightly aligned with the field, producing a tiny net attraction towards the field. Diamagnetic atoms produce tiny induced currents that oppose the field, so they experience a slight repulsion. On a planetary scale, these effects are extremely subtle and completely masked by other forces, but fundamentally, every atom follows the rules. Mm-hmm. Mm-hmm. Number of orbitals. Okay, okay. The number of orbitals in a is the sum of orientation. I believe that's the answer. Yep. You guys are okay. These are correct. These are correct. Now, how would I write these things into my note? That's the important part. Okay. Was I saw this table to draw the subshells, uh, the electrons in it with their own spin, but I saw that 3D was the far from so and the forest 4p 40 will arranged same uh, yeah, that makes sense, right? Occupation of orbitals. Mm-hmm. 3D, 4P, 5S, 4D. Mm-hmm. Aufbau diagram. Okay, okay. This is called Aufbau diagram. You did not mention this, brother. You did not mention this. Come on, come on, come on. I can't finish this today. Okay, I kinda got it. That's it. fuck is this? What? The fuck is wrong with you? Copy. No. Yeah, yeah, come on. Energy of the orbitals in multi-electron atoms. Orbitals in the same principal quantum numbers do not have exactly. What? Whoa, what the dude, my watch. Right, you got one job. To show me the time. That's my only single job for my smartwatch. And this guy can't do it. Brother. No two electrons in the same orbital. Mm-hmm. This makes sense. This makes a lot of sense. We have the D here, F here. For degenerate orbitals, same energy, example 2p orbitals. Okay, that's the Hund's rule. Okay, okay. I don't know if you guys could hear me chewing. I guess you guys could. Apologize for my chewing sounds. I'm chewing a set of gummy bears. Come on, come on, come on. Think, boy. Think. I got the Hund's rule now. I need to figure out how can I write those into my tablet. Come on. What are the most relevant information? Oh, come on, unlock. Unlock. God damn it. Oh shit, I gotta check one thing. Wait. How is it gonna be? Oh lord. No comments? What? I saw comments. Okay. What? That's five. Not I'm not talking five. I'm 6. Example 21. Is it 21? The first question? Yes. The solidus line is wrong in this case. The two substances are fully miscible in the solid state. That's what you showed is a solid liquid phase diagram with limited miscibility in the solid phase. Example 24. Just calculating. Oh, just calculating the average molar mass is not correct. Do the data analysis. Okay. With the help of regression line. Okay, I really appreciate the feedback. I gotta say that. That is precise and what I need to know. What? Okay. What was I thinking? Oh shit. How would I draw this one? One, two, three. Okay. One, two, three. Okay. Okay. Oh How would I draw this? This. Oh yeah, that's the only valid option. Eight. I don't know what it's called, but to explain this part on my note using an example. The alpha Where's my introduction to general chemistry? Mm-hmm. Mm-hmm. Wait, well, let me search in online like carbon's orbitals. Hmm. No, unhybridized carbon. The inner one is 1s. Let me just carbon 12, mass number, atomic number 6. If we start arranging, 1s, 2s, 2p, 3s, 3p, 4s, 4d, 3p, 3d. One S, 2s, 2p, 3s, 3p, 4s, 3d, and so if you got this, we could fill in the electrons. Got if we're drawing this in the Aufbau, here n equals 3. You see, we're stopping at 3p. So yeah, these are the orbitals that I filled. So 1s2, 2s2, 2p2, 3s2, 3p3. 10. That's for phosphorus, okay. Oh, 2p2. Okay, carbon is an example for paramagnetic. Can give me a we got 1s orbital, we got the 2s orbital, we got the 2p orbital. Oxygen, okay. Oh, neon, atomic number 10. Common paramagnetic element, copper. Nah, it's in 2 plus 8. Well, no, no, no. I'm gonna take neon. Okay. I'm gonna share the screen and okay, I'm gonna be explaining the how the principal quantum number, the magnetic quantum number, all are arranged for. I'm gonna explain with these two examples. I'm gonna write carbon 12, and neon. Oh shit, what was neon? Yeah, neon has an atomic number, and its mass number, atomic number, number of carbon is 6, atomic number of neon is 10. Okay, so first, yeah, first we're gonna arrange before. Okay, before we arrange, I gotta show how I and what my professor taught me to arrange the orbitals. It's like, let's take 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. And I believe it's good. Let's just write 5s. It's just gonna go like that. And we just draw an arrow from these, just crossing this. Now it don't start to make sense right now, but it will. So let's just take 1s, then we move to 2s, then we move to 2p, then we move to 3p, then we move to 3s, then we move to 3p, then we move to 4s, then we move to 3d, then we move to 4p, 5s, straight to 4d. How does it look? Let's just write 1s, 2s, 2p, 3s, 3p, 4s, 3d. I'm gonna write the rest down here. 4s. shit, come on. So 3D, then we're gonna go 4P, 5S, 4D, and we're just gonna continue, like maybe it's gonna be 5P here, yeah. So these go here and here. So for carbon, it's 6 electrons. 6 electrons. How 6 electrons are gonna be? 1s2, 2 electrons in s orbital, 2s2, 2 electrons in 2s orbital. So now it's already 4 and 2p2. That's gonna be in the 2p orbital. And now we got 6 electrons. Now for neon, it's gonna be 1s2, 2 electrons, 2s2, 2 electrons, and 2p6. That's gonna be for neon. Let's draw the Aufbau diagram. According to the Aufbau diagram, it's gonna look like 1s, 2s, 2p. It's gonna be again 3s, 3p, 4s. Just gotta draw the 3D. It's gonna be far 3D. Yeah, so 1s, we got 2 orbitals, two electrons in opposite spin. So we pair them up. 2s, the same. We pair them up. But for 2p, it's in a higher. We got three different orientation, like px, py, pz, and only 2 electrons are filled in the p orbital according to Hund's rule. Hund's rule, we only be filling in, like, we could fill in this way and just call it a day, but no, according to Hund's rule, we gotta make sure if we don't have enough electrons, we're gonna just fill each individual orientation with an individual electron. Now the same for 1s, 2s, 2p. The rest, just like the carbon, we're gonna fill in case of neon, two electrons paired, and one, oh shit. 1, 2, 3. And this time we got all 6 of them. 1, 2, 3, 4, 5, 6. Yes. Now we got all 6 of them. And here carbon is all electrons are not paired. Therefore it's paramagnetic. Now what does paramagnetic mean? It means that when an external magnetic field is applied to this to this atom, it's gonna orient itself in a way that it's gonna be attracted towards this magnetic field. But in the case all electrons, right, in the case of neon, all the electrons in the outer shell are paired. It shows diamagnetism. Now diamagnetism is when we introduce an external magnetic field. The electrons induce themselves in a way that they try to repel, but it's a really subtle effect that we normally wouldn't notice, but higher external magnetic field is applied, we could notice the repulsion from diamagnetism, or repulsion as part of diamagnetism, while paramagnetism is attraction to an external magnetic field. And this is happening due to uh, unpaired electrons in the outer shell, whereas in diamagnetism it's paired electrons. Now here, the principal quantum number is 2. The same goes for neon. The principal quantum number is 2. Because, yeah, we're at 2p. Right, yeah. That's what makes it. Now, from what I have understood, how the electron, how the atom is going to look like. Let's draw. This would be the 1s. This would be the 2s. And oh no. This would be the P 2p 2p, and as the only px and py are filled, we could say one of these would be px and one of these would be py. In the case of carbon, you could notice that z is not here, because the z orbital is not filled in. That's the reason the pz is not here. Yep. Now, in the case of neon, we could see the z orbital. Like, I don't know if I could draw it in a better way, but that would be the 1s. That would be the 2s, px, py, and pz. One s, 2s, px, py, pz. This is how the atom should approximately look like. And yep, that's what I understood about the atomic number, the principal quantum number, how it's arranged in the Aufbau diagram. This is the Aufbau diagram. Aufbau diagram. Yep. And yes, if I made any sort of mistakes, you guys could let me know in the comments. Oh shit. I think it should be good. That's what I understood. Periodic table. Here I come. Well, YouTube, it's 8 o'clock according to my timetable. Ho ho ho. You know, sometimes timetable comes handy. No, go to that day. Yeah. Week. Yeah. So it's already. Oh shit. Delete. 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 Yes, at 8 p.m. this should be over. Calendar. I did it. Oh, did I reveal my email address? I'm sorry, people. I know I'm stupid. Peace out, YouTube.